All right, today we're going to pull back the curtain on a really beautiful piece of mathematical magic. We're going to solve a problem that honestly looks completely impossible, and we're going to do it using a tool from a totally different part of math. It all kicks off with one very big question.
So here's the central challenge, right? Not just adding a few numbers, or even a million numbers. We're talking about an endless, infinite list of them. I mean, how could you possibly find a single exact answer to a sum that literally never stops?
And we're not talking about something simple here. Just look at this thing. This is an infinite series from a paper in Mathematics magazine. You're summing up 1 over n times n plus 5 for every single whole number n, from 1 all the way out to infinity. It feels like a job for a supercomputer, right? Well, it turns out we can solve it with a much more clever idea.
So let's frame this up. This is our puzzle. The challenge isn't just about getting close to an answer. It's about finding that one perfect, closed-form number that represents the entire infinite sum. And this kind of problem, it shows up everywhere, from pure math to physics, and it can be notoriously tough to crack.
Now here's the fun part. To solve this, we are not going to use any of the usual tools you might think of. We're actually going to borrow something from the world of engineering and differential equations. It's kind of like using a submarine to climb a mountain. It sounds crazy, but you're about to see how brilliantly it works.
So meet our secret weapon, the Laplace transform. What is it? Well, at its core, it's just a special kind of operator. It takes a function that's described in terms of time, and it transforms it, or kind of redescribes it, in the language of frequency. And the key idea here, which is explained so well in materials from places like MIT, is that you're not actually changing the signal itself. You're just changing your perspective. So one view shows you how a signal behaves over time. The other view breaks that same signal down into all the different frequencies it's made of. It's the same information, just a whole new angle.
So what does this transform usually do? What's its day job? Well, it does some real heavy-duty work. Engineers use it to analyze electrical circuits, to process signals. It turns these messy differential equations into simple algebra. What it's absolutely not known for is adding up infinite lists of numbers, which is exactly what makes this whole technique so surprising and so cool.
And here we go, this is the heart of the magic trick. We are about to use the Laplace transform to do something amazing. We're going to turn our infinite sum of separate, distinct numbers into a single, continuous integral. We're trading a sum for an integral.
So, drawing from the work of James Lesko and Wendy Smith, the whole method breaks down into 4 really elegant steps. First, we rewrite every single number in our series as an integral. Then comes the big move. We swap the order of the sum and the integral. This is the whole game, because it turns the complicated part into a simple geometric series, which is just a special kind of sum that we have a simple formula for. And finally, we just solve the one, much easier integral that's left over.
Okay, step 1 is this crucial translation. We take each fraction in our series and we represent it as this specific integral. Now, I know what you're thinking. It looks like we're just making it more complicated. But trust me, this new form has a hidden superpower that we're just about to unlock.
So, after we do this for every single term, our original problem, which was a sum of numbers, is now a sum of integrals. It might not look like we've made much progress yet, but we have just set the stage for the most important step.
And boom, here it is, the brilliant swap. We literally just changed the order of operations. Instead of summing up an infinite number of different integrals, we are now doing one single integral of an infinite sum. This move completely reframes the entire problem, and it's what makes everything else possible.
And what's the payoff for that swap? Well, look, the infinite sum that we created inside the integral is a perfect geometric series. And because of that, we don't have to add it up piece by piece. We can just use a simple formula to replace that entire infinite sum with one clean little fraction. All that complexity it just vanishes.
Okay, theory is great, but let's actually see this magic trick in action. Let's take a classic infinite series and watch this technique just solve it, step by step.
We're going to use this popular example, which is also in the paper. The sum of 1 over n times n plus 1. Now, a lot of you might already know the answer is 1. Maybe you've seen it as a telescoping series. But let's pretend we don't know that, and let's prove it with our new tool.
So we just follow our steps. We take each term, we rewrite it as an integral using the Laplace idea, and then we perform that magic swap. What you're looking at here is the result, one big integral, and sitting inside it, a brand new infinite sum that we now know how to solve.
Now, we just focus on that inner sum. And just like we talked about, that infinite geometric series collapses down into a simple fraction. 1 over e to the x minus 1. And just like that, the whole infinity part of our problem, it's gone. Now, once we multiply the remaining parts inside our integral, a bunch of stuff cancels out in a really satisfying way. The whole expression just cleans up beautifully, simplifying all the way down to just the integral of e to the minus x. It's a much friendlier problem to solve.
And when you evaluate that final simple integral, what do you get? You get exactly 1. The magic trick worked. A clean, perfect, whole number answer to an infinite puzzle. How cool is that?
So what's the big takeaway here? I mean, this is really cool, but it's not just about one clever trick for one type of problem. It's really about a deeper way of thinking about math.
You know, I love the way the authors of the paper, Lesko and Smith, put it. They're not just presenting some dry proof. They're sharing a new tool. They say they hope that you'll add this technique to your own toolbox for solving problems. It's such a generous and collaborative way to think about sharing mathematical knowledge.
For me, this technique really drives home 3 big ideas. First, just changing your perspective, in this case from a sum to an integral, can turn a ridiculously hard problem into an easy one. Second, it proves that math isn't made of isolated islands. Tools from one area, like engineering, can unlock puzzles in a completely different one. And finally, it reveals this really beautiful, deep connection between the discrete world of sums and the continuous world of integrals.
And this is not just some obscure one-off trick. As you can see from resources like MIT's OpenCourseware, the Laplace transform is a fundamental concept taught to engineers and scientists everywhere. It's a powerhouse for shifting perspective, and its applications, as we just saw, can be wonderfully unexpected.
And that, I think, leaves us with a final, really fascinating question. This whole elegant trick was found by connecting 2 fields of math that seem totally unrelated. It just makes you wonder, what other secrets, what other beautiful and powerful connections are still out there, just hiding in plain sight, waiting for us to find them?